So in the next chapter, quite naturally, we will talk about the derivatives of trigonometric functions. We will actually this semester skip the inverse trig functions and their derivatives. Instead, we're going to do quite a few applications of the trigonometric functions and how their derivatives can tell us more information about them. So first of all, let's think about how we would construct a derivative graph from that of a sine or cosine function. So first of all, this is my, let's say, sine of theta. What do we have as its derivative? Well, remember that if I want to draw the derivative graph, I have to think of the slopes of tangent lines of the original function and then graph the actual slope on the derivative graph. So for example, there are certain points where the slopes are easy to see. At pi over 2, I can see that the tangent line is going to be horizontal, which means that on the derivative graph, that will represent the slope of 0. So I have a point right here. Next time there's a horizontal tangent line is at 3 pi over 2, which means that 3 pi over 2, I'm also going to have slope of 0, and so on. Just like the sine function has this period, that means that the horizontal tangent lines will also appear periodically. Now, what is happening between, let's say, this point at 0 and this point at the slope 0? Well, I can see that at 0 the slope is actually fairly steep. In fact, it's the steepest it's ever going to be on the function, and then it gets less and less steep as we get to the flat point. I'm going to eyeball this as a slope of 1, so I notice that it's getting less and less steep as it approaches the actual slope of 0. What happens then is the slope becomes negative. At first it's just slightly negative, and then it becomes more and more negative until it's the steepest negative at pi. So I am going to approximate that this is going to be at -1, and then following similar logic, I will see that my function will curl back up and move around. What I notice, of course, too, is because the sine is the periodic function, the derivative of it will also repeat itself with the same type of period. So I know that I can repeat this pattern on both sides of my function. I also, even though it's a pretty rough sketch, immediately recognize this graph as actually the graph of cosine, which gives me some idea of the fact that the derivative of the sine function is actually a cosine function. So if I label this y, then this is going to be y prime. Now, this is by no means an actual rigorous derivation of the fact that the derivative of sine is cosine. In order to derive this properly, I would have to pull out the definition of the derivative, so the limit as h goes to 0 of sine of theta plus h minus sine of theta all over h, and then do a bunch of various trigonometric simplifications on that quotient. I'm not that interested in that level of rigor. I am more interested in really internalizing the fact that, at least justifiable from the graph, these two functions are connected to each other via the derivatives. If I start with the cosine as the graph, then following similar logic, I can produce the graph of its derivative. And I encourage you to actually go through this process to notice that the graph you're going to get is going to look something like this. And again, because it's a trigonometric function to begin with, the derivative of it will also repeat. And what we can notice is that the derivative in this case is negative sine of theta. So let's say we record what we have so far. The derivative of sine of, let's start using x, is going to be cosine of x. The derivative of cosine of x, we've just at least somewhat justified visually, is negative sine of x. And if we take these two things to be true, we can figure everything else out about other trigonometric functions using their relationships to sine and cosine. For example, if I would like to compute the derivative of tangent, I can first of all recall that tangent is actually sine of x over cosine of x. And that I can take a derivative of using the quotient rule and the derivatives of the sine and cosine that I have just come up with. Let's see how this would work out. So the quotient rule says, first of all, the derivative of the top which is the derivative of sine, which will be cosine, times the bottom, so times cosine, minus the top, so sine of x, times the derivative of the bottom. So the derivative of cosine of x is minus sine of x. So times negative sine of x, I will turn this into a plus right away so that I don't have to rewrite this entire expression. And then the quotient rule says to divide by the denominator squared. Excellent. Let's see what we have on top here. I have cosine squared plus sine squared. Well, I know that cosine squared plus sine squared is just 1 due to the basic trigonometric identity, which means that what I have altogether here is this expression is equal to 1 over cosine of x squared, or I know that 1 over cosine of x is actually secant, and because the cosine here is squared, I'm going to have secant squared x. This is then the derivative of tangent. The derivative of tangent is secant squared x. You can similarly derive the derivative of actually secant function to see that the derivative of secant will be, after some number of steps, after writing down that secant is 1 over cos and whatnot, you're going to get secant x times tangent of x. Okay? These are the main 4 trigonometric functions we're going to work with. The formulas for cotangent and cosecant are actually symmetric to these two and can be derived similarly, and you can always look them up to actually use them. Let's now try to see how these new derivatives work together with other differentiation rules that we have seen before, such as constant multiple rule, addition and subtraction rules, chain rule, and whatnot. So my first function here, I have a of x is equal to 4 sine x. So remember that constant multiple rule means that I can leave the constant alone and then take the derivative of the function itself. So the derivative of sine of x is just cosine. So overall, I'm going to have that the derivative is 4 cosine x. The next function here, I have tangent of 7x. Now I can see that the 7x occurs on the inside, which means that this is my inside function and tangent is my outside function. So as per the chain rule, I have to first take the derivative of the outside. So I first have to take the derivative of the tangent as a function. The derivative of tangent as a function is secant squared. And remember, according to the chain rule, when I take the derivative of the outside, I keep the inside as is. So first of all, I'm going to have secant squared, but with the same inside of 7x, times the derivative of the inside. So the derivative of 7x, which is just 7. Okay, I can of course rewrite this to be a little more familiar with the constant in the front, but this is just fine as is. For this next one here, I have sine cubed of x. Now this notation sometimes gets a little confusing because of where we place the power on the trig functions. So for the first few examples, I recommend rewriting it so that the power is visibly the power of the entire sine of x, because this makes it clear that now my inside function is the sine and my outside function is the power, which will then dictate the order with which I'm going to compute derivatives using the chain rule. The chain rule claims that first we actually take the derivative of the outside. The outside is the power of 3, which means this will come down to the front and the power will get reduced by 1. So 3 sine squared x times the derivative of the inside. So the derivative of sine of x, which is, as above, actually equal to cosine of x. Excellent. These are just the first few examples, and I strongly recommend that you practice a few more just to get comfortable with how to utilize other differentiation rules with the trigonometric functions. Here are a few more of the examples to really get comfortable with taking derivatives of these functions. Pause the video at this point. There is nothing here that is going to be completely brand new. You're just going to have to figure out which differential rules to use with the trigonometric functions in which direction, and then come back to see how to get through some of these. All right, so I'm going to leave some of the easiest ones for you to do. and I'm going to look at the ones that are a little bit more complicated. So let me try to get the hold of this number 4 here. Before we actually get into the computations, let's analyze what the function looks like. I have sine of the square root of x cubed minus 7x. So I have sine and then the square root and then a polynomial function underneath it. I have an outside function and an inside function, but my inside function has yet another outside function built into it. So I'm going to really have to be careful about applying the chain rule in order as many times as I need. So my most outside function is sine of x, which means that when I take a derivative of this expression, the first thing I have to do is take a derivative of the outside. The derivative of sine of anything is cosine of that same thing. So remember that I keep my inside intact. And now I have finished taking the derivative of the outside. I then have to multiply it by the derivative of the inside. So I'm looking at my inside function here, and I need to take a derivative of it. How do I proceed with that? I notice that, first of all, it is a square root, which means a power of 1/2. So my first rule to apply is going to be the power rule. 1/2 as a power comes down, and you subtract 1 from it. But then the inside of this function is yet another function, so I need to take a derivative of this as well. This is a really illustrative way to apply the chain rule. I'm creating a chain of dependencies up until I am done, right? So the derivative of this is going to be 3x squared minus 7. And once I have that, that is in fact the last function that I need to take a derivative of, because this in itself does not have an inside anymore. This is simply just x, my variable. So I'm done with taking the derivatives here. Be careful about making sure that you actually do go through all the steps and notice all the dependencies along the way. For the next one, let's take a look at this right here. I have ln of tan of x, so logarithm function of the tangent of x. So if I am to analyze this, I notice that my outsidemost function is the logarithm, and then my inside function is tangent. So in the taking of the derivative, I first have to take a derivative of the logarithm of whatever it has on the inside. The derivative of the logarithm of x is 1 over x, so it's always 1 over the inside times the derivative of the inside. And the derivative of tangent, which is my inside function here, is of course secant squared. Okay, and now I'm done. You can of course rewrite tangent as sine over cosine and secant squared as 1 over cosine squared, and then proceed to simplify the trigonometric functions as you will, but I am done taking the derivative, so I'm going to leave it as is. For this next one here, I have cosine cubed divided by 1 minus sine squared of x. So I could go ahead and take a derivative as is immediately using the quotient rule, but I can also notice a very familiar form, 1 minus sine squared. I know that according to the basic trigonometric identity, I can simplify this before I take a derivative, so I'm going to do just that. The top I'm going to leave as is, but according to the basic trigonometric identity, 1 minus sine squared x is actually just cosine squared x. Now I can notice that, of course, I can cancel out 2 of the cosines and end up with simply cosine of x. Well, taking the derivative of that is surely simpler than applying quotient rule and then power rule and then chain rule to this giant expression here. So the derivative overall is going to be simply minus sine x. Yet another confirmation of the fact that you should always simplify first before taking a derivative. This will save you a lot of grief in examples like these. Now, before we move on to the actual meaty, let's say, applications, let's take a look at a few that are purely mathematical. Finding equations of tangent lines to the trigonometric functions. So what I have here is find equation of a line tangent to sine x and then cosine of x minus 1 at the actual same point, x equals 0, and then we're actually asked to also sketch both of these functions and their tangent lines, just to get a visual support to what it is that we are expecting to see here. So first of all, tangent line, I'm going to need to find the slope of the line. If I'm after a line of any kind, slope is one of the properties that I would really like to find. And slope, of course, is a derivative. So what I need to do here first is take a derivative of my function. My function is sine of x. The derivative of it is cosine of x. And I am after the tangent line at 0. So that means that I would like to calculate the slope at 0. Slope at 0 is cosine of 0, which is going to be 1. And next up, I'm going to pull out my very, very helpful slope-intercept form, point-slope form, of a line and fill in the information that I have. So my slope is going to go into the value for m right here. And then I notice, of course, that I also need to figure out the corresponding point on my function. I know that x is equal to 0, so that's going to be my value for x naught here, but I don't know what the corresponding y value is. So before I proceed, I'm actually going to calculate y of 0. So I plug 0 in here, sine of 0 is 0, so I know that my corresponding value for y is also 0. Now great, I know that my slope is 1, so what I'm going to get overall is, look, this is 0, and the slope is 1. So I'm going to get y equals x. That means that the line tangent to sine function at 0 is actually a diagonal y equals x. Now let's produce a picture just to see if our conclusion here can be somehow also visually supported by the corresponding graph. So my function here is sine of x. So I'm going to have a 1 period of sine, and it keeps going off on both sides. And I am after constructing a tangent line at 0. So I'm looking for the line tangent to this curve at 0. And it's not hard to notice that indeed the line y equals x looks like it will mimic the shape of the sine function at that point fairly closely. So let's take a look at what it looks like if we actually use graphing software. Here's Desmos. In blue is my sine of x, and in red is y equals x, the diagonal. So as you notice already, it does look like it's tangent near the origin, but what is even more important is that it looks very, very similar to the sine curve at the origin. And if I zoom in, very quickly do I see that my red line actually sort of disappears because it is covered by the blue curve of the sine. They are so close together that you can barely see the difference already within simply 1 decimal place. And the further you move in, there you go. The red curve is entirely off the screen. All we can see is the blue sine curve being overlapped. So sine is in fact approximately equal to y equals x near the origin. And that is another very useful observation that I'm going to put down here. Sine of x is approximately equal to x for very small values of x. In fact, this kind of conclusion is the one that you can draw for the tangent lines of all kinds of curves, because indeed the tangent line mimics the curve near the point of tangency. And so here near the point of tangency is for small values of x because it's near the origin, and the tangent line is approximately equal to the sine value. So this is a good rule of thumb to remember, for example, in a lot of physics courses when you're asked to approximate things. Oftentimes small angles, the sine of them is approximated by the actual value in radians of the angle itself. The second question here is very, very similar, but now we're using cosine of x as our function. So again, because nothing about this process is new, please pause the video and go through this by yourself before seeing the answer. So as in the previous question, what I'm going to do first is take the derivative of my function, so y prime, and in this case, we're going to take a derivative of cosine of x, which is negative sine of x. What I need to do then is compute it at the point where I'm interested in, so at 0, which I'm going to get 0. And I also need to compute y of 0. I have my x coordinate. I need to plug it in to compute my y coordinate, which is going to be cosine of 0 minus 1. Cosine of 0 is 1. 1 minus 1 is 0. And then the rest of it is exactly the same as before. I take my point slope form of a line, and I'm going to plug in all the information that I found. So my slope is equal to 0, my x is equal to 0, and my y is equal to 0. Well, this is a pretty exciting equation, don't you think? Y is equal to 0. Let's see if we can sketch this and figure out if this matches our visual intuition. So I'm going to start with the function cosine of x and then move it down by 1 unit to actually illustrate this transformation. So cosine of x itself starts up at 1 and it's going to go down. It has a period like this. This is my cosine. So let me mark it, cosine of x. If I take the cosine of x minus 1, it means that I've shifted the entire function down by 1. So it looks like this. Okay, this end is a little bit crooked. There we go. And now, if I draw the tangent line at 0 to this blue function, I can of course notice that my tangent line is going to look like this. And that matches the fact that the tangent line algebraically comes out to be a horizontal y equals 0, the x-axis. Okay, so going through these examples, if the function looks easy enough to draw by hand, I encourage you to do so. Otherwise, pull up Desmos, draw your function, draw your tangent line to see that what you have is actually supportive visually of what you achieved algebraically. Let's take a look at an application. I've already mentioned last time that a lot of natural processes are cyclic, for example, on 24-hour period or the lunar cycle or the annual cycle. One of the easiest ones to track are heights of tides, and in fact, many places do track that because it's important for a variety of reasons. We have lots of data, and so I just pulled up data from the place named Tom's Cove in Virginia. If we just take a look at what the tides look like in that place, we can see that this is very clearly sinusoidal. This is one of the reasons I picked this place. The patterns here are just so symmetric and so perfectly sinusoidal that it's easy to actually model this function. So I took some of the data points and I came up by hand with a function that represents the tide heights of this place fairly closely. This is the function that models that. Once we have the function, we can predict a number of things and we can ask a number of things. For example, according to my function and according to the data, when is the tide highest and when is it the lowest? When is the tide coming in and when is the tide going out? What does it mean to take the derivative of it? What information would that provide? So let's take a look at how we can use our knowledge of trigonometric functions to actually analyze the heights of tide from the given model. First of all, the first question asks, when is the tide highest and lowest? This seems like it has a lot of information in it, so you sort of have to zoom out a little bit to notice one very important thing. This cosine is just one big chunk of this entire function. So if I were to describe this function to somebody in fewer words than written here, I would say it's 1.8 times a cosine of something plus 2.2. So immediately I know, for example, that cosine is bounded between -1 and 1, and that is something I can definitely use to my advantage. When is the tide the highest? Well, the tide is the highest when this quantity here is the biggest it can be. Now, no matter what is inside of cosine, I know that the cosine itself can never be bigger than 1. The maximum value of cosine is, in fact, 1. Now, I have to think about when does that actually happen. Now, I'm going to do that in conjunction of analyzing when is the tide the lowest. So first of all, I have to then think about when is cosine value the smallest, remembering that it can in fact be negative, right? So 0 is not the smallest the cosine can be. -1 is the smallest that it can be. So a minimum value of cosine is -1. Once I know that, all I have to do is figure out when does that happen. First, I can do something a little bit simpler and figure out what it is when it does happen. So the highest actual tide is what? Well, when cosine is 1, I'm going to have 1.8 times 1 plus 2.2. So I'm going to have altogether 4 feet. And the lowest tide is when the cosine is -1. So I'm going to have 1.8 times -1. So minus 1.8 plus 2.2 or 0.4 feet. This is also useful information to have, for example, if you're building a pier or want access to the water's depth at any point in time. Now let's think about when does that actually happen. What is the definition of cosine? Remember from the unit circle, cosine is the x-coordinate of the point on the unit circle. So if I drew a little unit circle on the side here we go, I can see that the highest that the cosine is, the highest x-coordinate is this point right here. Whereas the lowest that it can ever be is going to be at this point right here. This is the value of 1, which will produce the highest tide. This is the value of -1, which will produce the lowest tide. Okay, and now all I have to do is then figure out when does my angle equal either of these two. Once I have stripped away the fact that cosine is the x-coordinate, all I have to work with is its actual inside. Okay, let's record this real quick. So maximum value at angle 0, minimum value at angle pi. So what am I going to have? My angle on the inside then for the maximum value has to equal to 0. So I can set pi over 6 t minus 11 to be 0 and then solve for that. Now this is not going to be too difficult. I can see that t is in fact 11 and t is hours after midnight, so I know that this is 11 a.m. For the second part, I need the angle to be pi, so I'm going to set whatever is inside the cosine to be in fact pi. So all together, then I have this expression, and if I solve it, I will get that t is equal to 17, which in hours after midnight means 5 p.m. Now, one thing you have to be careful about, and I'm going to leave it for you to ponder, is, are there others? One thing that is difficult and you have to be careful about with trigonometric functions is the fact that they are cyclic. So just because the angle happens to be at these 2 points doesn't mean that these are the only options for those angles. If I go for another roundabout, I will hit the same angles but with a different measure. So I will hit the 0, I will hit this point again, but not at angle 0, but rather at angle 2 pi. I will hit this point again, but not at angle pi, rather at angle 3 pi. So think about how will we compute these various other occurrences of the needed angle and how many of them I have to actually take care of. Okay, think about that. This is a little bit of the homework for you. Let's take a look at the second part of this question here. Find and interpret h prime of t. Okay, so what we have to do, first of all, is take the derivative of this expression. What are we going to have here? Once again, it's probably best to zoom out and think of that as just the cosine value. So altogether, first of all, what I have is the constant that I'm going to leave as is, 1.8, and then I have the derivative of this giant cosine. The derivative of cosine, which is the outside function here, is negative sine. So I'm going to pop a negative up front, and I'm going to have a sine. I'm going to keep the inside as is, and then multiply by the derivative of the inside. This is my inside, so I need to multiply by the derivative of it. This is also not too hard. Remember that t is our actual variable, so this number is a constant times the variable, and this 11 is actually just a constant. So overall, the derivative of the inside is going to be just pi over 6. What are the units and what is the meaning of this actual expression? Well, the units for the derivative, if we would like to write it in the other format, is dh by dt, and then we can read off the units as whatever the units of height is divided by the units of time. So this will be feet per hour. And of course, the meaning of that is this is the rate of change of tide height at time t. The rate of change of tide at time t. Now, there are a number of other questions that one can ask, and in particular, one question that is connected to the first one here is, if we know when the tide is the highest and the lowest, what about when does it come in and when does it actually come out? This is the third part of this question here. What we can do is think through how we've obtained these points and what does that mean for the movement between highest and lowest, or we can also take a look at the graph of this function here. This is the graph of this function that I've actually come up with an expression for as the model for the corresponding data that I've collected. If this is the graph of my function, let me first of all label this through. So we said that time was in hours after midnight, which means, for example, that right here, this is 5 hours after midnight, this is 5 a.m. This highest point up here is at 11 hours after midnight, so 11 a.m. This point I can see at 17, which means 5 p.m., and this point up here is going to be at 2300 or 11 p.m. So this already justifies why you should be looking for more points here to answer the question, when is the tide the highest and when is it the lowest? So this is a little hint to your previous homework exercise here. But from the graph and from just thinking about what happens between local, or in this case global, maximum and minimum of a continuous trigonometric function, I can see that the tide is coming in between 5 a.m. and 11 a.m. because that's when the height is increasing. It's also coming in between 5 p.m. and 11 p.m. What do those time intervals mean in terms of the derivative? So for both of these regions, what is it that I can say about the derivative? If the tide is coming in, it means that the rate of change of height of the actual tide is positive, which means, of course, that the derivative on these regions at any point between 5 a.m. and 11 a.m. and 5 p.m. and 11 p.m. is in fact going to be positive. Now, of course, the question can be phrased in the opposite direction. For what hours is the tide going out? And that will give us the other time periods. I mean, on the graph here, the one I can see fully is between 11 a.m. and 5 p.m. Of course, that means that the height of tide is decreasing, which means that the derivative on this region is going to be negative. I would like to highlight the fact that remembering the definition of the cosine as coming from the unit circle will give us a lot of different ways into answering trigonometric function questions like these. Also, having access to the graphs will be a very good visual support for our solutions. So please go through and see if you have any questions, as well as think about what other questions might be asked and how you would approach them. Let's take a look at another application. This one doesn't come from the real observed data, such as the heights of tide from the previous example, but we were going to model the temperature of an outside swimming pool that basically follows the hours of sunlight and night, and therefore also follows this kind of sine pattern. So what we have here is the overall temperature, where T is in degrees Celsius and little t is in hours since midnight. And we have a few questions here. When is the temperature the highest and the lowest? Find and interpret the derivative of the temperature. And during what hours is the temperature of the pool increasing? Again, you have all the tools here, so pause the video and try to go through this question by yourself. So, as I already mentioned, given the definition of sine and cosine, there are a number of different ways that we can approach these problems. Normally, when we read highest and lowest in calculus, we think about the global minima or maxima. However, with trigonometric functions, there are much simpler tools that we can use, such as the fact that they are going to be bounded by the unit circle. So, for example, let's think about what is the highest possible temperature here. The highest temperature occurs when this subtraction is the smallest number possible, right? So notice that I have 25 minus some number. So the total is going to be largest possible when I'm taking away the least possible amount. So now I have to think about what can the smallest value of sine be. So the highest temperature, let's record this. Temperature is going to occur when the sine value is smallest. And we know that any sine of anything at all is always bounded between -1 and 1. So this sine value is going to be smallest value at -1, right? So sine value is the smallest, really means that sine is -1. And now I just have to figure out when that happens. So thinking back to the unit circle, let me make a quick sketch here. When is sine at -1? Sine is the y-coordinate. The y-coordinate of the -1 is going to happen right here. And this is going to be 1 pi by 2, 2 pi by 2, 3 pi by 2. So this angle right here is 3 pi by 2. So sine is -1 when the angle is 3 pi by 2. Notice that here our angle isn't just t though, our angle is pi t over 12. So that means that I need to solve for when pi t over 12 is equal to 3 pi over 2. And this is a fairly straightforward arithmetic. You're going to get out that t is equal to 18. Now remember that t is hours since midnight, so 18 hours after midnight, which means it is the warmest at 6 p.m. Take a look at how simple it was to analyze this without ever attempting to take derivatives or employ calculus, and by simply using the definition of the sine function as being the y-coordinate of a point on the unit circle. I'm going to leave the lowest for you to do. Is going to follow the exact same structure. There's going to be nothing terribly different about it, so I trust that you're able to follow through. The next question is asking to find and interpret the derivative. So let's go ahead and take the derivative of my temperature here. So first, the derivative of 25 is, of course, 0 because it's a constant. And then I have -4 times sine. So -4 is going to stay. And now I have to carefully apply the chain rule. My outside function is sine. So first of all, my derivative is going to be cosine of whatever it was that I was given in the first place, times the derivative of the inside. So now I have to take a derivative of this value. Now remember that t is my variable and everything else is a constant. So this is like taking the derivative of pi over 12 times t, a constant times t. The derivative of that is just the constant, so pi over 12. Now we're asked to also interpret this. Let's first of all think about the units. So it's the derivative of big T with respect to little t. The units of big T are in degrees Celsius, and the units of little t are hours. So this is Celsius per hour. And in terms of interpretation, remember that the derivative is simply the rate of change. And here what we're seeing is it's the rate of change of temperature at any given point in time. So in this particular case, at time t. At time t. And finally, we're asked, during what hours is the temperature of the pool increasing? So increasing is, of course, a specifically calculus concept of when the derivative is positive. Okay, so let's remember that t is increasing, or any function is increasing, means that the slope of the tangent line is positive, which means that the derivative is positive. So now I have to actually use the expression for the derivative that I have just derived. So what I have is minus 4 cosine of pi t over 12 times pi over 12 has to be positive. When does that happen? Well, I should probably clean up what I have in there, right? So I can multiply everything by -1/4. This will flip my inequality sign. And I can also divide everything by pi over 12. So overall, my expression is going to become cosine of whatever angle I have. Modifying the inside of a trigonometric function is difficult, so we're not going to do that. And then it's going to be less than 0. Okay, so notice that I skipped a couple of steps here of getting rid of the constants. And because one of them was negative, my inequality sign got switched from bigger than to less than. Okay, so now I have to think about when is the cosine of something negative. And again, back to our trusty unit circle. Cosine is the x-coordinate of the points on the circle. And this is asking when is the x-coordinate of the point on this circle is going to be negative. The x-coordinates of the point on the circle are going to be negative, between these 2 points, right? This is where my x-coordinates are in the negative side of the x-axis. So between here and here on every single rotation. So that means that whatever angle I have, which is pi t over 12, has to be between pi by 2, which is my top point here, and 3 pi by 2, which is my bottom point there. And now I can solve this entire expression for t in the middle. So I can get rid of pi's all over the place, and then I can multiply by some kind of constant, and you will see that in the end, your t is going to lie between 6 and 18. So that means that the temperature of the pool is increasing between 6 and 18 hours during the day. Comparing this to what we got in part 1, saying that the temperature is the highest at 18 makes sense. The temperature is increasing all the way from 6 a.m. to 6 p.m. It's going to reach the maximum right before it starts dropping towards the night. I encourage you to sketch the graph of this function just to reconfirm that these findings match what the graph is telling us to match. And also notice, of course, that because this is going to be on a 24-hour clock rotation, what we're going to see is the same graph repeating over and over again with the new cycle of the sine function. This next question about breathing, I am going to leave to you. I encourage you to go through both of the parts and think about how the sine actually is representing the breathing of a person that is very cyclical in nature. And let's take a look at this application for the blood pressure. I encourage you to look for various links on YouTube to find reading about the systolic and diastolic blood pressure and how the heart actually works and how that pressure is actually measured. We're going to focus on the mathematical model here. So generally, in the most general of terms, the human heart goes through the cycles of contraction and relaxation. And during these cycles, of course, the blood gets pumped from the heart out and back in repeatedly. Overall, the blood pressure can be modeled by this function for a particular person, right? So of course, every person is a little bit different. So the constants that are embedded in this function are going to change from one person to the next. The question doesn't actually ask us to do math. The question asks us to think about what kinds of questions can one ask about trigonometric models like these. So pause the video for a minute and see what kinds of questions can you come up with. For example, if you were creating an exam question that involved this function in this context. So I have a few examples here that students have given to me in the past. For example, one can ask, when is blood pressure highest or lowest? And this would involve the same analysis as we've done before on the largest and the smallest values for the cosine. You can also ask, when is the pressure increasing or decreasing? And that would involve taking the derivative, finding out when it's positive or negative. You can then even ask, when is pressure increasing the fastest? And that would involve some kind of second derivative analysis. Think about a variety of questions that one can ask and how you would approach them, given the fact that the model is trigonometric, what kind of tools we've developed, and what kind of things you can both ask and answer about these functions using particular calculus tools.